This video will cover the Gram-Schmidt process. This process is really just a formula. So when you're given a set of vectors, like v1, v2, v3, all the way up to vn, all you do is just apply this formula that's on the screen. So you set u1 equal to v1, and then you kind of find u2 by applying this respective formula. Then you find u3 by using this formula. And you do that for all of the vectors up to un. This formula will actually be shown to you probably in two different ways. This is the first way, and the other way is this one. So both of these formulas actually mean the exact same thing. If you recall, the projection formula is actually, the formula for the projection is actually this over here, this dot product sort of thing. So these two formulas mean the exact same thing. And what the Gram-Schmidt process does, after you apply the Gram-Schmidt process to this set of vectors, what it does for you is u1, u2, u3, all of those u vectors, those will form an orthogonal basis. And that's the goal of the Gram-Schmidt process. These first vectors, these original vectors, they did not form an orthogonal basis. They may have formed a basis, but it was not orthogonal. Orthogonal is the key word here. If the question wants you to find an orthonormal basis, all you do is you apply the Gram-Schmidt process, and then you take each vector and you divide it by its magnitude. So I would take u1 and divide it by the magnitude of u1 so that I could normalize that vector. And that would give me, if I did that for each one of these u1, u2, all the way up to un, that would give me an orthonormal basis. All right, so that's the formula. If that's all you need, then there it is. If you would like a better explanation on and a little bit more in depth, continue watching and we'll go over that right now. So to begin with, where we want to begin is the orthogonal projection, actually. That's where we want to start with. And I really like to use this website. It's like math.gatech.edu. The link will be in the description. So if you want to check it out for yourself, feel free to check it out. It's always very helpful in my opinion. So what we're dealing with here is, first, before we get into the Gram-Schmidt process, we want to determine how to even find an orthogonal projection and get a really good understanding of what that means. So what's kind of shown here is we have this vector x and this vector u here. And what I'm going to do, or what's already done really, is they've taken x and they've broken it up into two components. One component goes in this direction, and then the other component goes in this direction. And the goal is to find actually this component. The reason why we want this component is because if we take x and then subtract off this component, that'll leave us with the orthogonal component. So really what we're looking for is the orthogonal component. But to find that, what we need is we need the component that is in the direction of u. So what we'll do is we'll take x and we'll project it onto the vector u. and that'll give us this component. And then all we're going to do is we're going to take x and subtract off whatever that component is, and we'll be left with the orthogonal component. So this formula right here, this is the projection of x onto the vector u. So all these vectors really should have the little vector symbol above it. To save time, we're just not going to use that. Right? This is the projection formula. So that's where it comes from. If you want to have a better understanding of the projection formula and where it comes from, you can try and look up some things about the projection formula. It has to do with the fact that you're taking kind of the magnitude and the direction into account. So right, we want this magnitude, but we want to make sure that it's in the direction of u. So that's the projection. And once we have a good understanding about that, then we can, the Gram-Schmidt process almost follows directly from that. So this is the part about the Gram-Schmidt process. Right? And we can see we have that exact formula here, right? So what you do to begin with always is to start with your first vector, and then you get your second vector by just applying the formula. And then if there's a third vector, you apply the formula again, right? And you just do that until you're out of vectors. That's really all there is to it. So I think with that, we can go ahead and move on to a few examples here. So yeah, let's go to this example of two vectors. So here we have vector v1 and v2. v1 is 1, 1, 0, v2 is 1, 1, 1. And we want to find the orthogonal basis for w, which is spanned by these two vectors. This is kind of the type of question that is generally asked when dealing with the Gram-Schmidt process. So before we actually apply the Gram-Schmidt process, before we actually apply this formula, since we're dealing with these vectors that are in 3 dimensions and there's only 2 of them, what we can do is we can actually visualize this. So let's look at the visual before we apply the Gram-Schmidt process. So here we have our first vector. This is our first vector, v1, and this is our second vector, v2. And we can see that in order to find an orthogonal basis, all we do is we first declare our first vector to be the first basis vector, right? So we need to start somewhere. This is arbitrary. This is the only arbitrary step. We could have also defined v2 to be u1, right? In that case, we would be trying to find a vector that points in this direction, or perhaps this direction, right? We would just need to be finding the vector that's orthogonal to v2, right? And then our formula would be kind of different. But that is a viable solution when you're finding an orthogonal basis. That is completely an acceptable solution. But generally speaking, we just let whatever vector we're given first be the first vector. So here we declare u1 to equal v1. And what we're looking for is we're looking for the orthogonal component right here, right? In order to find that, what I want to do is I want to take v2 and I want to subtract off the component of v2 that goes in the direction of v1, right? So I want to subtract off the projection of v2 that goes in the direction of, I should say actually here, u1. That goes in the direction of u1. And these vectors are actually kind of conveniently set up so that this projection actually equals v1. So that won't always occur. This is a special case for this particular problem. So if I just take v2 and subtract v1, that will give me what u2 is. And let's check that to make sure that's right. So here's v1, here's v2. I'm going to take v2 and subtract v1. So v2 is 1, 1, 1. I'm going to subtract v1. That gives me 0, 0, 1. And that is the answer. That's the same thing, right? That's what they got when they did the projection, when they applied the Gram-Schmidt process, right? So the reason why I wanted to go through this problem is because when the dimension is low enough, you don't need to apply the Gram-Schmidt process. If you, right, you can have just the visual interpretation, right? We can just have the visual interpretation, and that's good enough, right? We can determine, okay, if I just take v2 and subtract v1, I'll be left with the orthogonal vector, and that's all I need to do. So that was a quick way to just, instead of doing the Gram-Schmidt process, to skip it. If you did the Gram-Schmidt process, you would get the exact same answer. For this next one, we start with the first two vectors are actually the same as the previous problem. So it's the exact same problem. We're just adding a third vector here. And again, let's look at the visual interpretation. So this one's actually kind of hard to identify what's going on. So remember in the previous problem, we had already found vectors u1 and u2. So let's start with that, right? Because this problem kind of builds off the previous one, right? Remember u1 was equal to v1. So this is where v1 lies. And then u2, remember u2 came from doing v2 minus, really it's the projection of v2 onto u1, right? But we just found that that was just v1, right? So if I had to draw v2 somewhere in here, I would think it's somewhere in this direction. I would think v2 is somewhere in that direction. But let's continue on, right? Once we have u1 and u2, right, the next thing that we want is this u3 vector, right? We want the vector that's orthogonal to both of those original vectors, right? The vector that's going to be orthogonal to both of those is the one that's coming out of this plane that's formed, right? So that's why we're looking for this vector right here. We want this vector to be orthogonal, right? So v3 is coming out here. What we need to do is we need to subtract off this component from v3. So we need to take v3 and subtract off this component. Now that component is actually pretty interesting because it has two components itself. It has one component in the direction of u1 and then one component in the direction of u2. So we actually need to subtract off two things right here. One is the projection of v3 in the direction of u1, and then the other thing is the projection of v3 in the direction of u2. We need to subtract off both of those. And that's exactly what the Gram-Schmidt process tells us to do. And if you apply the Gram-Schmidt process, right, we'll get u1, that's our first vector, u2, we already got that from the previous problem, and then u3, if you apply the projection formulas, you'll get 1, -1, 0. And so all three of those vectors, these three vectors right here, form an orthogonal basis for the original set of vectors. All right. And then moving on to the last problem here. We have three vectors, but now they're in dimension 4, right? So this is pretty much why the Gram-Schmidt process is written as a formula rather than like stated as like a visual interpretation. This is because when we're in dimension 4, when we're in R4, there's no visual interpretation for it. We can't visualize vectors in dimension 4, right? On this page, they don't have a visual interpretation for it. Right, so you can't represent these vectors in dimension 4, or you can't visualize it. But we still want to be able to form an orthogonal basis. So this is where the Gram-Schmidt process comes in handy. It's for any dimension where we can't visualize what's going on. So this is where the Gram-Schmidt process comes into play, right? So we just apply it. We set our u1 equal to v1, just our first vector. Then we take u2 is going to be v2 minus the dot product of v2 dotted with u1 over u1 dot u1 times u1, right? That's the projection of v2 onto u1. We want to subtract off that projection because this is the component that lies in the direction of our first vector. So if we subtract off the component that is in the direction of our first vector, we will be left with a completely orthogonal component. And I guess we get some pretty nasty fraction in there, but that's totally fine though. That's a completely fine answer. And then for U3, we do the exact same thing. So we just need to subtract off the component that lies in the direction of U1, and then we subtract off the component that lies in the direction of U2. And what we'll be left with is a vector that is completely orthogonal to U1 and U2. That's all there is to it, really. So then those three vectors form an orthogonal basis. And again, if you want an orthonormal basis, all you need to do is take these vectors and divide them by their respective magnitudes. All right, and that about covers it. This is the video on the Gram-Schmidt process, and that's it.